In this video, we shall see an example on how the linear system is going to behave. Okay, so for that, the A matrix which we have taken is, which is in this form. Okay, A is some number. Okay, and these two things are 0 and this is -1. Now the question is, what is the phase portrait, okay, for different A value? Okay, so where the A can vary from -infinity to infinity, and for these different values of A, how the phase portrait is going to look like. So that's what we are going to see. Okay, say let's use this A and write it in this form, and we will get this equation. And if you see, I can write this equation into this form, where the x dot doesn't depend on y and y dot doesn't depend on x. Okay, so such a case is known as uncoupled. Okay, so now how to solve this one? Okay, so that's solving this one is an easy procedure. So once we solve it, what we will get is this equation, these equations. Okay, so how x is going to vary and how y is going to vary. Now let's see how y is going to vary. For some initial value of y, which is y0, what's happening to y as time progresses? It is getting towards 0. It's diminishing, right? So that's what happening to y. But what's happening to x, we can't say. So we have to make some assumption on A. Okay, let's say A is some negative value. Okay, so if A is some negative value, then what will happen to x? X will also go towards 0. So in this case, y will also go towards 0. When A is negative, x will also go towards 0. So finally, the system will end up in a state where both x and y are 0. Okay, so that's an equilibrium point. Fine. So for this system, 0, 0 is always an equilibrium point. Okay, and for linear system, that's the only equilibrium point. Yeah, right. Now but how the phase portrait looked like? So even before we calculate what is identify how the phase portrait is going to look like, let's take a value of A which is less than -1. Okay, if A value is less than -1, then y will decrease at a particular rate. Okay, but x will decrease very fast when A is less than -1, say -2. Okay, the next value will decrease very fast compared to y value. Okay, so for that case, the phase portrait will look like this. Okay, so if you see, say this is my x0 and y0, the initial position, right? Then the x is rapidly decreasing. Okay, and after it decreases enough, only then y starts dominating or showing its effect. Okay, so this is how the phase portrait will look like when A value is less than -1. Okay, what if A value is exactly equal to -1? If A value is exactly equal to -1, then the rate of change of x as well as the rate of change of y are same, okay, they'll be diminishing in a same rate. If that's happening, then the phase portrait will look like this, okay. And this is also known as since this picture looks like star, so this particular point is also known as star node, okay. Fine. So now what if a is still negative but greater than -1? If it's greater than -1, then this will diminish very fast compared to x, okay. So if that's the case, we will get some kind of this picture but in a flipped manner, which is this picture, okay. So here y is decreasing very fast, and the decrease in the x is slow, okay. Now what if a value is exactly equal to 0? If a value is exactly equal to 0, then this whole term e to the power of at will be 1. So x of t is always equal to x naught. So that it means there isn't any change in x value, but y value is diminishing, okay. So if that's the case, then what will happen is this. So there isn't any change in x, but y value is approaching towards the line y is equal to 0, okay. So this sort of behavior is known as line of fixed points, okay. Now what if a value is positive? If a is positive, then what's happening to x? Instead of diminishing, it starts increasing, which means it starts going away from 0, okay. If x naught is positive, it's going towards right, and if x naught is negative, it's going towards left, okay. So it's increasing. But what about y? Y will always decrease and try to reach towards 0. For that case, the phase portrait will look like this, okay. If you see here, say this is my x naught and this is my y naught, okay. The y naught is decreasing towards the y value decreasing from y naught to 0, but at the same time the x value is increasing from x naught to, and it's moving towards infinity, right? The same goes for this one, okay. But when x naught is negative, it's going towards -infinity, okay. So this behavior, okay, this is one behavior when a is positive, okay. Now, so these are the fixed points. If you see, we have fixed point at x is equal to 0 and y is equal to 0, and this fixed point is known as the fixed points are also known as node, and this is a stable node, this is a stable node, and this is also a stable node, because if we give a little disturbance, it will come back, okay. This one, it's a line of fixed points, okay. If we give a little disturbance in this direction, it will come back, but if we give a little disturbance in this direction, it will assume its new state along this direction, but still y will be 0, okay. So that's what this this system represents, okay. And how about this one? it seems like stable along this line, but it's unstable anywhere else. If I give a little kick, okay, and say the system goes like this or like this, okay, and it will try to go away, okay. So it's not exactly stable, but at the same time not unstable, okay. This is known as saddle node, okay. So this kind of equilibrium point or fixed point is known as saddle node, okay. And as an exercise, what you could do is, instead of assuming this value -1, assume it as a just 1, okay, and try to identify the phase portrait for different cases of A, okay. So yeah, so I'll leave that as an exercise. Thank you.